Right. So, yeah, welcome to this panel discussion, which concludes the day for today. I don't think I need to introduce the panel members because you've all seen them give their talks today. So we have Graziella Gelmini, we have Matthäus Hostert, we have Ivan Martinez-Soler, we have KS Babu, and we have Kev Abazajian, who are all experts in the topic of this discussion session, which is BSM physics in the neutrino sector. And I think before we start with dedicated questions to our panel members, let's see if there's any burning issues from today that you, the audience members, would still like to bring up. Anything that you didn't get a chance to ask after any of the talks today? Any comments you have about the topic of BSM physics in the neutrino sector? Yeah. Wait, where is it? Let's use this microphone. Yeah.
I think it was in your talk you were showing the unitarity triangle, so to speak, of the neutrino sector.
Yeah.
And I was curious, like we know in the quark unitarity triangle, we need to go to sub% to find new physics. Is it realistic to think that this neutrino unitarity can be brought down to that level of precision, sub%?
Sub% seems challenging to me. I mean, we'll have percent level measurements of the oscillation parameters soon, but sub% is a tall order. So I don't think we'll achieve in the foreseeable future. I don't think we'll achieve the sensitivity that we are seeing in the quark sector. But maybe one of the panel members is of a different opinion and would like to comment. Ivan, you've done global fits.
Yeah, I think probably we won't get there. It won't be a one-to-one with the CKM, but maybe that doesn't matter. So should just keep testing. That's my approach.
Is there some expectation as to the level of deviation from unitarity? I mean, at what level should we expect it? Is it sub% or anything will do?
I have no idea. I'm just saying, look at what we do know, which is the quark sector, where we know it's sub%. Do we have any expectation in the neutrino sector that it should be larger than that? Like, or is that sort of like the target? Yeah.
I mean, that expectation in the quark sector is coming from the fact that we have this notion that new physics needs to sit above the TeV scale in order to avoid existing collider limits. Now, in the neutrino sector, it's much easier to hide also light new particles because they don't need to be charged. So maybe the requirements for discovering new physics are a little bit more relaxed in the neutrino sector because even lower mass things are not as firmly ruled out yet as they are perhaps in the quark sector. But that's, of course, a bit of a hand-wavy argument I'm making here.
Regarding to the unitarity thing, I mean, I think in the future, not this generation, but maybe the next one, we will have a higher chance just to see something. In particular, if you make this complementarity between different experiments, we have IceCube that is going to have a huge precision on the mass splitting, but also in several other parameters, and that can be very, very interesting for I mean, the next generation will be maybe the next one. I mean, the interesting.
I'll also point to Andres' talk the other day, where he talks about over-constraining the parameters. So that would be one way that you could argue for unitarity tests, is a way to over-constrain the parameters to see if oscillations and our three neutrino paradigm is indeed correct.
So even if we don't get there, I think it's still good to compare with what we know in the quark sector and see how little we know in the neutrino sector.
Okay, are there any other questions that were like left over from the day that you'd still like to bring up at this point? I don't see any. So then the first question I'd like to ask our panel members is, in your opinion, is how likely or unlikely is it that BSM physics will first show up in the neutrino sector? So are we looking in the right place? What's your take on that?
I'd say it's the only place BSM physics has shown up, so I think that'll be the next place it will show up. That's my opinion.
Yeah, I was also going to ask what exactly is BSM here stand for? Would identifying that the neutrino mass ordering is inverted, would it count as BSM? I think it would be very exciting to see if the mass ordering is inverted, because it would be more counter example compared to.
Yeah, indeed, I tend to agree with that.
Well, in the standard model, the mass of the neutrinos is not explained. So 3 neutrinos is just the flavor of solution is BSM now. But I think we have several scenarios. For instance, if you consider the minimum excess at very low energy, doesn't fit very well with the 3+1 scenario. And in order just to explain that, if we rule out or not or whatever, at the end of the day, we will have a signal that once you count in the global analysis, it doesn't fit very well with the sterile one. And it seems like maybe the explanation seems to be other models. It might be involved sterile neutrino, but I think it's we are looking to the correct direction in the sense that we are having several anomalies, and not all of them are easy to explain.
But one could make the argument that, for instance, also quark flavor physics has several anomalies, and they do have consistent explanations that at least explain some of the anomalies and are consistent with all other constraints. I think for the short baseline anomalies, we're having difficulty with that, like finding something that explains more than one anomaly plus all the null results.
Yeah, I agree. If your prior is anomalies, then actually one could argue that it's probably not going to be in the neutrino sector. And if the prior is not the experimental anomalies that we have, then I don't know what it should be. So, yeah.
It's difficult to say where the BSM will appear first. Actually, have no idea. This is why the strategy of a very wide net is what works best. But I think in the neutrino sector, if you see a failing of unitarity, this has to go someplace. The issue is that I don't know if you will know where it goes. If it goes to a sector or so on and so forth. So you may suspect, as in the case of neutrinos have mass, so there is something more. But I do not know if we are going to know what more there is. For example, it would be absolutely revolutionary to try to detect the sterile neutrino. All these ideas to detect the sterile neutrinos, I think they should be pursued in the laboratory. They should be pursued. I mean, this is absolutely essential. And they're relatively cheap experiments. They are not, LHC-like or any like that. And the other, of course, is if neutrinos are Majorana or not, which we don't even know. And all these things are related to the neutrino sector. Now, the problem is that we may still know, as with the case of the masses and mixings and so on, that there is something more, but there are so many different explanations. It's so hidden, this hidden sector, that we may not know what is the BSM, because we already know that there has to be some BSM. In the standard model, neutrinos are massless, but we don't even know if the right-handed neutrinos, the sterile neutrinos, are there or not. And so it is to be seen, but maybe in the next 20 or 30 years, before we say, well, we just say, well, this is not possible. There is a lot to be done still, and it's difficult. I mean, we may be lucky and discover dark matter someplace. If we are, but
we've been lucky a couple of times in the neutrino sector, right?
So I think looking at the wording of the question, when Fermilab G-2 experiment have more data, and they could be announcing further results by the summer. So there is a good chance that the anomaly, if it becomes more than 5 sigma, for example, that could be claimed as BSM, first solid evidence of.
I think the problem there is will we end up with a similar situation in the neutrino sector? I think even if the G-2 anomaly goes beyond 5 sigma, most of the community will probably not call that we now are sure that there is BSM physics, because we still haven't been able to put our finger on what exactly it is. So to some extent, there is a danger that a similar thing will happen in the neutrino sector. For instance, the mini-boon anomaly is almost 5 sigma. If you combine it with LSND, it is beyond 6 sigma, I think. But of course, no one would claim that this is now firm and solid and uncontrovertible evidence for new physics. So is that a danger that we are running into the situation that we are maybe even seeing new physics, but we won't be absolutely sure that it is new physics? Is that a danger? And if so, then yeah, what could we do to gain that confidence? Of course, that will depend on what exactly it is we are seeing, but. Matthias?
I didn't have anything to add to that, no.
No, I thought Matthias was asking for the microphone.
Yeah, I agree with that comment. And for me personally, I think models where you can test the supposed new physics that would explain, for example, mini-boon in a completely orthogonal way are very important. Because if you hit something in this completely orthogonal way, then you can be sure that that what you're seeing is new physics. Otherwise, if we keep doing, for example, same short baseline with similar systematics, it may be much harder to.
Can you give an example for one of the models you have in mind? I have an idea of what it's probably going to be. But.
Right. So light dark sectors, for example, I can find those mediating forces elsewhere, for example, in colliders or fixed target experiments.
Right. So. Okay, would anyone from the audience like to make a comment on that? Yeah, Ornella?
Yeah, I have a sort of a comment here. Of course, we all hope to be in that situation and to find BSM physics. I think, though, unfortunately, there is a part on which we need to work a lot, which is understand better that when we do not now, and we discussed this yesterday, neutrino interactions. Because if you don't do that, and as soon as you don't do that, you can also see something, but you will never know if it is related to, let's say, standard neutrino interactions or something different. So I think we need to work a lot. And
I wouldn't say you will never see it, but it's definitely much harder. For instance, if you see a clear oscillation signal.
Oscillation, yes. Yeah, no. The oscillation was.
But usually that we're not that lucky. Sure. And then, of course,
the signal for oscillation is very clear. But all the other BSM type that we discussed this morning imply that you know very well how the neutrinos behave. And until you don't do that, unfortunately, will be difficult to disentangle.
Yeah. So, indeed.
That's it's not a good comment to make, but unfortunately, it's an important point.
Who goes first?
I had a follow-up question about that. In dark matter searches, they're about to run into the neutrino for I don't know. I say about to, but I don't know if it's 20 years or 5 years. These attempts to improve our understanding of neutrino nuclear interactions, is that something that could be used to improve our understanding of the neutrino background in dark matter and therefore, so to speak, lower the floor? Or is it too complicated of a problem so it's hopeless?
Who wants to take that one?
If you hold it, it turns red. The red is on.
It was on before.
Okay, thanks. Probably others are more qualified to comment on this, but my assumption is that the neutrino floor that you're worried about in dark matter experiments is not the same type of process that you're worrying about in accelerator experiments. These are much more challenging energies, and in the dark matter side, you're talking about coherent scattering at low energies. It's much easier from my understanding. And we will also have a lot more data on that with lab experiments, reactors, and PIDAR sources?
You know, in the community now, we talk about neutrino fog instead of neutrino floor, because floor is sort of, you know, something definitive that you cannot get through, but it is more a fog. It's a background that you have to, depending on the spectrum, and it is only irreducible if you have a particular mass, a particular spectrum, and so on for the dark matter. But if you have others, the spectrum is different, and so you may get through. It's a background to work through. Now the issue is how much working through background you are going to do. But in so doing, these experiments will really measure the spectrum, and it might be that some NSI, I mean, I haven't seen this, I'm not an expert in NSI at all, but here there are some experts on NSI. Has this been worked out actually? How the spectrum that could be seen in dark matter experiments, in this huge multi-ton new generation dark matter experiments would be changed with some NSI? I mean, I am expressing my ignorance, but that's what I thought it came to my mind, because actually you can use this opportunity. These detectors will really measure this in a different manner through neutrino nucleus interaction.
You know, I can't add to this, but people have done studies of whether you can see effects on this neutrino floor or neutrino fog if you want. And I think the answer is yes. You know, these dark matter experiments will get to a point where they'll actually see something, which is neutrinos, and they can actually study these neutrinos whether they want to or not, because the neutrinos will be there. And there's some work that goes in the direction of asking what good can come of this, in quotes. And I think looking for these new interactions is one easy way to look for that. Yeah, absolutely.
I think a rather general qualitative comment in this direction is if the new interactions are mediated by relatively heavy particles, then it's mostly a normalization change. But even that may be interesting because we understand the normalization of solar neutrinos to at least the 10% level. But even more importantly, if the new physics is mediated by some light new particle, like a dark photon or whatever, or even as for the magnetic moments by a standard model photon, then you see that the spectra rise steeply towards low energies. And that's exactly where the dark matter community is doing a great job. And then you can expect really spectacular signals that would not have shown up anywhere else. So that there are papers on that look into this.
I'm showing my ignorance of this, but I think that this is very important, because actually they are going to measure in trying to pass through the fog. They're going to measure that, and actually, it might be if there is an NSI or something that you know, after all, the spectrum is not so degenerate with what you would expect from dark matter, and that would change things also from the standpoint of trying to detect dark matter itself. So the interplay is there. And these experiments are going to be done. So, you know, it's a great opportunity for this community to actually, but I didn't know that all that much work, I mean, has been done already in this regard.
Yeah, there are several papers. There's also the fact that you have to compete with the lab experiments doing similar measurements with sources like pi on the key at rest and reactors. But in the case of the solar neutrinos, I'm not sure anyone has explored this, but there's the fact that you don't get new taus coherently scattering in lab experiments, but you would in the case of solar neutrinos. I'm not sure anyone has explored that. Yeah. There's certainly complementarity between the two.
No, if we are lucky, we are going to see not only solar, but we are going to start seeing at some point atmospheric and so on.
Yeah.
Depends how much work is because at some point experimentalists vote with their feet, and they stop doing experiments right when it becomes too costly, difficult. The return is not there, and so on and so forth. We're not there yet, but they will reach probably the atmospheric neutrinos too.
And I think it's very interesting in the sense that the low energy part of the atmospheric neutrinos are going to be a background for the measurement of the DSMB, for instance. And I don't know how well we know that part. I mean, how many experiments has measured with a huge precision this part of the atmospheric neutrino flux? In the future, okay, we have super K, but in the future we will have better experiment, better detector, so a better possibility to constrain that flux. That is a background for new searches, and that will be very, very interesting, in my opinion. I don't know. No, yeah, but I mean, you are able to measure the binary part. I mean, it's true that, yeah, you can make an extrapolation, you can make a prediction for the.
So from a historical point of view, that's an interesting discussion, because if you remember how dark matter direct detection started, soon after there was the proposal by Witten. There was a paper pointing out that the abstract went something like: a recently proposed neutrino detector by Studolsky and company, by the way, is also a great dark matter detector. Then all of this became the field of dark matter detection, and now we're writing papers saying, oh, by the way, these dark matter detectors are also great neutrino detectors. Yudai, you still had a comment, right?
Sorry, my comment and question is more for point 2 and 3, so we can wait until then. Sorry.
Yeah, then let's wait until we get to that.
Yeah.
I take the important mic. I take the mic from people who matter. Very good. So one person's fog is another person's signal. That's an obvious statement. And actually, it would be very interesting to know what the solar neutrino spectrum looks like at these energies measured with coherent scattering, even in the absence of NSI. I mean, this is an interesting measurement. And depending on what you measure on the high energy, if you can get to HEP neutrinos, for example, which we have not seen, that would be an interesting measurement. And of course, as you mentioned, DSMB, I mean, when they draw the neutrino floor, they say atmospheric, DSMB. I mean, if we were actually to see DSMB, there is an entire field where people are very excited about this. So I would not dismiss the floor at all as the floor. That's all.
As I said, if you want to be in the know, you don't call it the floor anymore. Now it's fog. It's a joke. It's a joke. It's a signal for some, but in the community of dark matter detection, it's fog. I think it is more adequate.
It's good for these experiments to have a signal.
Yes, that is also true. You're rather pessimistic. That might be the case. No, I'm not pessimistic. Yeah, they will for sure see that.
So maybe this is a good moment.
I think we have a question at the back.
Oh, where? Ah, Anna.
Thank you. I just wanted to follow up on Alex's comment. It might be very hard to detect DSMB in dark matter detectors unless we are very lucky and the flux is pretty high because of the atmospheric neutrinos.
They write the atmospheric DSMB, and that means that the upper limit for DSMB is close to what the atmospheric is, and then when we see a signal in that region,
So is that because when super-K and hyper-K are looking for the DSMB, they do so in UE, whereas a dark matter detector would also be sensitive to the nu component of the atmospheric flux, which is much larger? Is that the reason?
So, the reason is kind of with inverse beta decay, it's almost like 1-to-1 relation between energy of neutrino and then the positron. But with the dark matter detectors, they see just the recoil. Let's say they can see recoil energies. So in that case, neutrinos with like 10 MeV or neutrinos with 50 MeV, they are almost likely produce the low recoils.
Right, yeah.
So all the atmospherics are smeared over to lower energies.
So
thanks.
What's larger in the end, solar or atmospherics? Because I would imagine boron 8 also overwhelms your
Yes, so solar, they like end at around the 18 MeV, and the SNB can extend to larger energies.
I see. Okay.
But even though like normally in the bare fluxes, you have kind of window because atmospheric neutrinos extend to much larger energies when the cross-section is higher. And also you tend to produce always low recoils, then it smears over the DSNB.
One question. So you mentioned the recoil, that you will measure just the recoil. And we know that the incoherent interaction is affected by the quenching factor that we don't know very well what is the. If we improve that, for instance, that uncertainty, do we have any possibility to use this kind of measurement to detect the SNB? Or, I mean, what are the uncertainty that we have? Or they are killing us there? Because you mentioned, hey, you measure the recoil, yeah, but I understand very well what is the recoil, and I can predict it very well, and I know that the prediction, one of the uncertainties, the quenching factor. So do we have any expectation for that?
I would think that still it's pretty hard because as you go to larger energies, at least the cross-section seems to saturate.
Okay.
And the atmospheric flux peaks at around 1 GeV. So you still can have like a large contribution until hundreds of MeV, depending on what is the nucleus that you're looking for. But I don't think that could help. Maybe some inelastic thing, but yeah, I'm not sure.
Okay.
What do we know about the SNB of all players?
Sorry?
This is the bound on the SNB of all players. Okay.
Mm-hmm.
What do we know in time? Not very much. Just some assumption about oscillations.
Mm-hmm.
Infer things that we know are.
Mm-hmm.
So for the remote audience, the question was, what do we know about the DSNB in all flavors? I mean, I don't know who wants to take that. Anna?
Yeah, I think so far we don't know that much. We have the limit for nu bar from super K around, let's say, 3 in centimeters to the -2 seconds per -1. And then nu E is around 19 in that units. And then current limit on X flavors from super K from scattering on electrons is like almost 1,000 in these units. So the coherent detectors can help to reduce that depending on the exposure to like around maybe the same limit as for the electron flavor now, but it's hard to get detection unless we are lucky and the flux is pretty high.
But there are some bounds, already some bounds on the. Yeah, there are some bounds from Super K looking for the DSNB that already set in the around 20 MeV. Said we have looked for. They use hydrogen tagging, and I think they.
Yeah, Michael?
The super K limits are derived under the assumption that the electron anti-neutrino flux is 1/6 of the total flux. So that's the assumption. That doesn't mean that the electron anti-neutrino flux is 1/6 of the total flux, but that's the assumption that is made. So and I think there's also a limit from snow on the that uses electron neutrinos rather than electron anti-neutrinos.
Okay, I think that's maybe a good moment to move to the next question, which is, in the hunt for BSM physics, how do terrestrial neutrino experiments fit into a broader context? So maybe we can discuss a bit the interplay between what we do in terrestrial experiments and what we do in other BSM search strategies, in cosmology, in astrophysics, or also in non-neutrino experiments like flavor physics, colliders, and so on. And we've already heard a bit on that today, but I was wondering if maybe the panel members can each give their take on that, like where do you see most complementarity, where do you see the most overlap, like if there is new physics in the neutrino sector, where do you think where else we should look for that kind of physics?
Well, in cosmology, and I guess we might hear more tomorrow, but verifying or detecting that n nu in the relativistic background is 3.044 or not is going to be pretty important. So if you detect something else, it could be neutrinos, it could be something else that's relativistic. So I think that's going to be an indication of new light degrees of freedom if it deviates from that. There's some recent helium results that says n nu is less than 3 now. So the helium crisis is back, or the BBN in crisis is back. George is giving a thumbs down. I'd love to hear your opinion on that.
Do you want to comment, George?
You won't like my comment. So I'm not going to believe primordial helium until we measure it in the CMB. So as you well know, this linear regression of 20,000 compact blue galaxies, of course, it has tiny statistical errors, but the claim that we know helium to the precision that is claimed in, for example, that Empress 2 paper that just came out, I'm sorry, I just don't believe that.
Can you comment on how we can see that?
I'm not an astronomer, so I don't. You can take my comment with a big grain of salt.
Can you say how that could be seen in the CMB, since you said you will believe it once it's seen in the CMB?
Yeah, I mean, with polarization data, they can, especially EMO polarization, they can tease apart the ineffective and primordial helium content. The basic physics reason is that the more helium there is, the more baryon number is on neutrons, so the fewer the number of electrons. So one thing that the CMB people can certainly measure is the mean free path of an electron, of a photon. And so that's sensitive to the electron density. Just a word of pessimism from me.
Is that something that CMB stage 4 will be able to do, or is that?
Yes, stage 4 will get the helium abundance, the claimed helium. The claim from the science book, the stage 4 science book, is better than 1% precision on primordial helium, and simultaneously better than 1% precision on ineffective. Now, right now, Planck has constraints on both of those, but they don't have good polarization data, and so they're not able to get both of those simultaneously to that precision.
Yeah, both are, I guess, 1/3 of 10%, 3% or so, at least for ineffective. I was going to say the same thing. Right? The next generation CMB experiments are going to be able to yet again test BBN to be accurate. So it worked. Deuterium predicted the baryon to photon ratio when I was not even a grad student. I was visiting UC San Diego, and Tytler's group was measuring D to H, and that was then confirmed by WMAP. But now we're going to at the same stage for helium. So.
Neutrino-less double beta decay, as we all know, provides complementary information to oscillation data. I think it is very fundamental because if it is measured, it's a violation of lepton number, which would be the first observation of a lepton number violation. And I think an interesting scenario could be that neutrino-less double beta decay is observed in the next generation, and the long baseline experiments find normal mass hierarchy. That means
what do we do then?
Yeah, what do we mean? I think there is an interesting connection we can make with LHC physics, because in this case, the neutrino-less double beta decay is not dominantly coming from the neutrino mass itself. So there could be some interesting prediction for LHC in that scenario.
So you're saying then there needs to be some other source of lepton number violation that via the Schechter-Wallis theorem contributes to neutrino stability.
At the current level of sensitivity, the new physics scale should be afforded TeV in order to contribute enough to neutrino-less double beta decay. So that will be a very interesting scenario for, and it brings in synergy between different types of experiments.
Yeah, indeed.
Or we're missing something in the oscillation measurement. Could be either way.
Yeah, that will be good to be in a confusing state for a while, but we will sort it out.
I mean, another interesting aspect is like with the terrestrial experiment for some BSM scenarios, it's impossible just to get some precision or to explore some particular mixing for some BSM scenario that we are not able to explore in terrestrial, but we will be able to in astrophysical experiment or something like that. For instance, we're talking about pseudo-Dirac scenario, but for instance, the decay of the neutrinos, if we want to explore lifetime that are or the order of 10 to the 5 seconds or even larger can be explored in astrophysical sources. But in the Earth, since on terrestrial experiments seems to be very difficult because of our limitation that we have. So that's another complementarity.
Right.
Well, if I have to make any comment, I would say that neutrino experiments nowadays have replaced, in most parts, this old idea of looking for light particles with intensity. So very rarely you find an experiment nowadays that is doing beamed up style searches without being at the same time a neutrino experiment. So something like SHIP, for example, is what you would build if you wanted the ultimate beamed up experiment, and it just turns out it's also a neutrino experiment, right? So that happens a lot, not just with accelerators. And I guess the only exception would be electron beam experiments, such as like LDMX or NA64, where you're looking for missing matter. So yeah, I think we're quite lucky.
I think that casting a wider net as possible, as wide a net as possible, is absolutely essential, because I think where we are, well, maybe there will be this absolute unmistakable signal someplace, but it is also very likely that we are going to learn from incompatibilities or mismatches between different data. No? Something that I think will be extremely interesting is also to measure the spectrum of CMB. It hasn't been measured since Kobe. You mentioned Kobe. Kobe measures virus, the spectrum. And, you know, at some point, well, anything that can leave an imprint, even from before CMB, I think that thermalization time is 10 to the 6 seconds, something like that. Anything that happens after 10 to the 6 seconds should leave an imprint of some sort, even if it is minute, in the spectrum, deviations from the thermal spectrum. But I don't think that, maybe you know, I don't think that there are plans to measure, but I don't think that there is anything approved to measure that spectrum again. Isn't that so? But this would be absolutely essential, because then you will see features. I mean, at some point there has to be deviations from the thermal spectrum of CMB.
And in various contexts, BSM scenarios are constrained by that measurement. For instance, I remember that there's some region of the dark photon parameter space that is excluded by the measurement of the CMB spectrum, right?
Yeah, but this measurement is from
That's from Kobe, right? Yeah.
From Kobe. It hasn't been done again. And now they could have, you have to go enough orders of magnitude down in the precision in order to have all sorts of information about things that happen that would leave an imprint in the spectrum, the shape of the spectrum. And as I said, experiments such as, I'm still trying to say, like Hunter, right? It's a long shot, of course it's a long shot, but they are not terribly expensive experiments. Yeah. And together with Tristan, it's measuring in a range in which you don't have other experiments that measure the parameters of a sterile neutrino in that range. I think they are essential. I mean, we cannot put, you know, a laboratory experiment is an experiment. Yeah? Either you find it or not, it is there, it's not there. If you find something, the revelation could be, I mean, the payoff is so big that I think this investment should be done.
Yeah. So since we will still have time to discuss the complementarity between terrestrial and especially cosmological observations tomorrow, and looking at the clock, I would actually like to move on to another question that I think is very important that we discuss it, and that's whether, in your opinion, BSM physics has been adequately taken into account in the design of current and upcoming experiments, and if not, where should we improve? So for instance, when you look at the Dune proposal, the physics case for Dune is made via the measurement of leptonic CP violation. And as exciting as that measurement is, there's of course many more things that Dune can do. Has that been adequately taken into account in your opinion? And if not, where should we improve?
This may be controversial, but I don't think so. I think the near detector complex could be much better. If the plans that we have, if the most optimistic scenarios that we currently have go through and we get all of that, great. Could still be better, but that's good enough. But I'm not sure we are in that situation.
But that means the full near detector complex with ND-LAR and ND-GAR.
Exactly.
You already know that we are not going to get that on day one, right? So,
right, exactly.
Yeah, I wholeheartedly agree with that comment.
I think, I mean, coming back maybe to what we discussed yesterday, but regarding the cross-section measurements, some of the BSM scenarios predict some cross-section that are not, I mean, some modification of the neutrino cross-section that you need to take into account, for instance, all the, not only the total cross-section, but also the differential cross-section, how the outgoing particle, the energy that we have, how they are emitted, just in order just to explore in detail these scenarios. And I think in many of the scenarios that we are exploring, those details has not been taken into account. How we can do that? Well, we have an event generator, but we have to improve that and include the BSM scenarios into those event generators. That will be very, very helpful. And I think we are still a bit far from this scenario. That would be useful.
I also completely agree with that. If peers can implement their BSM scenario in a generator, I think there could be more results produced. At the moment, I think they are also in a user-friendly way.
So what we are missing is the mad graph of neutrino physics, right? But I think that there's people working in that direction. Who is it? I forgot who it is. But yeah, there is people working in that direction.
Yeah, I don't have much to add. I've not looked at these experiments in this way.
Yes. I see several hands up. I think Udai was first.
Yeah, thanks a lot. So yeah, directly related to your statement. So it is kind of important. I think it's an interesting time now. All the generations say that, but now we're really the time that we have to design the next generation colliders, and also we're in the snowmass process, and also Dune is being constructed. So directly related to the Dune near detector. So as what Matthias said, a lot of these dark sector search are actually neutrino experiments, including the previous one like CHARM and NuCal. And these are actually neutrino experiments, but they have decay detector, like going to be the gas detector. So these things are truly important. But beyond that, you can also have the symbiotic detector that is also located in the hole, like for example, searching for mini-charged particle. And these kind of things, even though they're very low cost, they can be added with a low cost and use the beam facility. So I think that's something that, of course, we want the Dune to get built as soon as possible, but that's also something that we can consider along the way. And also reversely, because we're building the collider like ILC, hopefully, or any kind of a linear collider or the HC. There are clever people in Irvine that design this forward physics facility for neutrino experiment. So these are, broadly speaking, BSM search, but they can also be used for neutrino ILC as well. You can do a beam dump for ILC. So those things, I think, is good for the neutrino community to discuss more and really think like for the theorists to sometimes think like experimentalists. I think it's very useful because we could actually help find the best location or the best design. Of course, we cannot do it ourselves, but to help them to search for this, it's very important. Yeah, thanks.
Let's see who was next. I think Andre, right?
You know, I also wanted to add to what Matteo said. You know, this is a very important question. I think the challenge is that today we don't have any clear model that we would like to test decisively. I think that's the challenge. However, what I think we need to keep in mind, and that's something that I worry about when I look at next generation experiments, is flexibility. You don't want to paint yourself into any corner and then regret it, 20 years from now. You would like to be able to respond to some unexpected discovery that could happen, and you don't want to be in a position to say, wouldn't it be great if we had this kind of a detector in the near detector hole, and then just to find out that your near detector hole is too small, or something stupid like that. So that's the real worry, is not to. I think it's we can't make the case that we need to have a super duper gigantic near detector facility today, but we would like to have the flexibility to respond to some anomaly or some discovery in a way that doesn't require you building a whole new infrastructure and blah, blah, blah. So that's what I hope the people up above who are making sure these things can happen, that they keep in mind and they don't throw away opportunity that we might regret in the future.
I 100% agree. Though I have a feeling that people don't like excavating empty space.
I think you should have the flexibility with the apparatus you have. I just want to remind people that Kamioka was not designed as a neutrino detector. It was designed as a proton decay detector, and they had the flexibility to change it. I think that's the most important thing here, to have the flexibility.
But it does pay off to have a detector that does more than you designed it to do, just to be on the safe side.
I think it's an important discussion. I think it's maybe two components that are somewhat implied. One is the detector's capability or the facility. The other side is also the analysis and tools to make use of those detectors. And an example maybe that's at the interplay of the two is triggering, for example, which obviously the LVLXC is a very much pressing topic in terms of not making sure you don't miss things that you'd want to look for. And I think it's something that is worth stressing as well.
I want to ask the high energy experimentalists here. So people in IceCube, for example, or KM3net, what are their plans for flexibility and BSM searches? Because that's an interesting area where you're not probing the same energy region anymore, right? So as we look into more and more astrophysical neutrino events, there's lots of potentials for surprises there.
So who wants to comment on that?
I think it is already as flexible as it can be, right? Because you are, so the way that the detectors are currently designed is they are looking for fluxes, right? That's they are discovery experiments. So either IceCube at this point or Gen 2, they are designed in a way to find the flux. That's the first thing. And whatever comes with the surprise there that you're saying, then is the ability of you to exploit the statistics and systematics that come with it. And that's the maybe a painful part, because where you have enough statistics, which is the low energy part of the story, you don't have enough systematics. And where we are better in terms of resolution and like reconstruction, you don't have enough statistics. So this is the sad part, but I think the good news is that multiple detectors are coming up. So that could compensate for what we lack in order to do BSM stuff with a very high energy part of the story. So if we have IceCube continuously running, then Gen 2 is there. So the core is still there. So you still have data at lower energy, more data at a higher part of the spectrum. Then KM3net is there. It's going to do supposedly a very good job with the oscillation measurements. then there might be P1, and there's also the radio detectors that can expand this energy range. I think we all hope for this surprise here, but I think if eventually we would be able to pin down the features in the spectrum, we probably have a very good chance of going after BSM with a better like analysis. So let's put it that way.
I'll just add to that that the most immediate path to BSM that I can see in the highest energy experiments is flavor identification and identifying the flavor fractions of the neutrinos that we're seeing. And that's currently severely limited because our particle ID is not great at the highest energies. And so I think if we first build better tools to identify the right flavors, and I will talk more about that tomorrow, but you can see smoking gun signatures for new physics just by identifying the flavor fractions of the astrophysical neutrinos. And that will also become an even stronger tool as the terrestrial experiments constrain the oscillation parameters better. And so in the next 20 or 30 years, we're going to see a scenario where you know your oscillation parameters well enough that you can not only identify the emission mechanism at the sources of these high energy neutrinos, but also if there's any new physics in their production or in their propagation or at the detection at the detectors. And so that is the most, I think, exciting part of the next 10 or 20 years.
Okay, so looking at the time, I think we're almost at the end of the discussion session. Is there anyone who wants to make one final comment, either from the panel or from the audience? Kev. Yeah, the last question is one that is perfectly suited for being discussed over drinks and dinner.
It's the most important one.
Okay, then every
I'm
panel, let every panel member summarize in 1 or 2 sentences what their most exciting BSM discovery would be. And then we go from there, yes. And then we'll see every panel member has to sit at a separate table, and we see who attracts most of an audience.
X-ray detection of dark matter.
Excellent.
X-ray. Yeah. Yes. Well, I can be biased.
Yeah, for me, it has to be the proton decay. Although it's the same neutrino detector, which is going to.
So the most exciting place, I think, low energy neutrinos of the order of MEV or something like that from the astrophysical source can be very interesting just to see what we get. I mean, nothing that we know.
Yeah, I really haven't really thought about this too much, but the first thing that comes to mind would be neutrinoless double beta decay detection. So you know that you have something to play with on the model building side. That would be interesting. So I agree with that.
I think that the most important is the one that will be made. Anyone that will be made will be absolutely important, because who knows? I mean, even at the LHC, right? We are sort of discounting the LHC already somehow, even if there's an open. Well, not for neutrinos, but she says BSM. Oh, well, this neutrino physics or neutrino physics. Well, neutrino physics. Well, to me, there are two things: sterile neutrinos and neutrinoless double beta decay. Because even if it will be extremely interesting to see a violation of unitarity, you may not know what is. I mean, we may be still in the dark. We know that there has already neutrino masses indicate that there is something else. And we have no idea what it is. Lack of unitarity, measuring very well all the parameters may not lead us to understand what is next. But if there will be one more particle, If you know that, or if you know that neutrinos are Majorana, I mean, this would be absolutely, these two, any of these two would be, for me, I mean, from outside, of course, I'm not a specialist in this kind of thing. But.
I think neutrino beta decay would finally vindicate everybody who has to suffer with their colleagues telling you that neutrino masses are not BSM.
Okay, wonderful. So thanks a lot to Graciela, Mateusz, Ivan, Babu, and Kev for this wonderful discussion. And thanks to all the audience members.